All right, guys, let's get started. So I believe everybody is here for seminar in computer architecture. Right, great. So I'm Mohammed Al-Sir, and I believe you are here in an interesting and fun class where you will learn how to critically review and present scientific paper, fundamental and cutting-edge papers in computer architecture. So before starting, I believe all of you have taken the digital technique course before. Okay, good, good. So I'm going to introduce or talk briefly about why we need to study computer architecture, just to set the stage, and then I will be talking about the logistics of this course. And since you have taken the digital technique course, so we don't need to explain more details about or introducing the computer architecture topics. All right, so computer architecture is the science and art of designing, selecting, and interconnecting hardware component, as well as designing the hardware-software interface to build the entire system that meets some specific goals, such as functional, performance, energy, consumption, and cost, and many others more. And some of those are more important than the other goals, depends on the application needs and demands. And an enabler has been Moore's law, and I believe all of you are familiar with Moore's law, right? Okay, good. So I don't need to harp on it. So basically, Moore's law expect the component counts to double every other year. So this is a figure from the paper showing that the number of a component or transistor that can be integrated or combined in an integrated circuit over the year. So you can see there is an exponential increase in the number of transistors over a linear time. This is another figure from the same paper where you can see per specific year. So as this is the relative manufacturing cost per component, and this is the number of components per integrated circuits. So as you increase the number of those components per the same chip or the same wafer, then the cost per component is going to drop. And you reach some point where you hit the capacity wall of that chip. So you can no longer increase the number of component or transistor unless you get a larger wafer or you scale the technology. And basically by scaling the technology as the time progressing, so this the point where you hit the capacity wall, it gets shifted. So you can see here we are able to increase the number of transistor or component per integrated circuit much higher than previously. And this is another example showing that the Moore's law is still applicable even up to 2011, but it's still applicable even nowadays. However, it's going to reach a point that it's no longer be applicable very soon. So this is the paper. Honors Motlu recommends to go through this paper, just 3 pages long, and it was written on 1965. And there are 2 important quotes from this paper. So the first one, by 1975, economics may dictate squeezing as many as 65,000 components can be integrated in a single chip. So you can see the beauty of technology, and it's very beautiful to enable this technology to accommodate more transistor and more. The second quote is it possible to remove the heat generated from integrating this large number of components per single chip? So maybe this is in 1965, it wasn't a big problem, but these days it's really huge and serious problem, especially as the technology is scaling, so you're able to integrate more than 2 billion transistors per single chip. So why study computer architecture? Right. This enables better systems. So for sure, we want to design a computer that's faster and cheaper, smaller, and more reliable. And this is happening by exploiting the advances and changes in underlying technology and circuit. So it's very important to understand what's going on at the circuit level. So computer architecture is not about hardware, but you need to combine both software and hardware solutions in order to specialize the architecture in hand. And this enables you to have new applications. So you may think about applications, but there are many more applications that are unimaginable. For example, 20 years ago, we don't have lifelike 3D visualization, for example. But these days, we are very close to have it. And still, people are attempting for that. Self-driving cars are another example. Personalized medicine, genomics, machine learning, and many more applications. So by studying computer architecture, also we are able to enable better solution to problems. For example, we don't want to use general purpose processor for example, for bioinformatics or big data applications. So by using specialized accelerators such as GPUs, FPGAs, or maybe processing inside the memory itself, this sounds something interesting, rather than using some energy inefficient solutions. And for sure, we need to understand why computers work the way they do. You cannot improve something if you don't understand the mechanism or the underlying circuit or the architecture behind it. So computer architecture today is a very exciting time to study those topics, to improve it and having or enabling more applications. So industry in a large paradigm shift to go, for example, to many core solutions. For sure, many core solution means stamping out more cores, right? So it doesn't seem as a good solution. So we want to do something inside the processor itself, inside the core. We want to change it. We want to have a new architecture or having specialized accelerators next to the core or next to the memory or near storage and so on. However, this paradigm shift causes many more challenges and problems. For example, huge hunger for data and new data-intensive applications, power, energy, thermal constraints, as well as complexity of the design. So it's no longer a simple architecture. You have heterogeneous architecture where you have many processors or many accelerators. So this for sure will increase the complexity and programmability of such architecture. And technology is not scaling well for sure. So you have challenges, for example, row hammer problem, where you can flip part of the memory or some bits in the memory and then disturb those section of the memory, then you have serious security and reliability problem. And many more challenges as well. So for sure, no clear definitive answer to these problems. These problems affect all parts of computing stack. And you are familiar with this computing stack from Digital Technique course. So you need to address many challenges from the user side as well as the underlying architecture side. So users are always demanding, and users 20 years ago have different demands than today's users. The architecture as well, as long as we are able to scale the technology, having more challenges. So we need to address all of those. So computing landscape is very different from 10 or 20 years ago. We need to do something to rethink this computing stack from the user perspective or software and hardware layers. So every component and its interface as well as entire systems design need to be re-examined and rethink. So this is an example of heterogeneous architecture where you have GPUs, FPGAs connected to the memory, can do processing maybe inside the memory at the logic layer, or persistent memory storage as well. If you understand both the hardware and the software, you can revolutionize the computer, the way we build the computers. You can invent new paradigm. Nobody stopped you from doing that. You don't have to follow the existing architecture. You can come up with new architectures for computing, communication, storage as well. This is one of the book. Onur Mutlu recommends you to read it. It's The Structure of Scientific Revolutions, and shows 3 cycles for any scientific field. It's not necessarily computer architecture, and shows many examples from different fields. So the first cycle is pre-paradigm science, where no clear consensus in the field. You don't have clear theory that can explain the observations you get from new architecture or new paradigm. Normal science, dominant theory used to explain those observations. So Onur Mutlu believes that we are in the pre-paradigm science, where you are free to do new architecture and new system designs. The third cycle is revolutionary science, where underlying assumption needs to be re-examined. So this is the author of this book, this very beautiful book, and this is the 2 versions of the book. So it's highly recommended to go through it. And if you don't like reading book, you have this technology. All right, so the main takeaways from those slides, it's an exciting time to understand and design computer architecture and maybe new paradigm for computing, storage, communication, and so on. By shifting this paradigm, you are going to have more challenges, more problems you need to address first to enable those new technologies and new applications. And for sure, by having or enabling those new systems for biological stuff or medicine or machine learning, you are doing high impact or huge impact on the world. This is for sure driven by huge hunger for data. These days, we are able to generate a huge amount of, for example, sequenced DNA from our bodies, but we are still unable to analyze efficiently those DNA to discover new disease or discover personalized medicine. For sure, this is driven by significant difficulties in keeping up with the hunger and technology layers. We have 5 walls, so energy, reliability, complexity, security, and scalability, and many more. So increasingly demanding applications, if I give you the requirements, so as a computer architect, you can dream about the architect that meets those application needs. And human beings are good dreamers for that. So this is an example about 64-bit double precision floating point complex operation, where it consumes about, you can see here, 20 picojoules. However, a single read or write operation to the DRAM consumes 16 nanojoule. So it's about 800x more energy consumption than the operation itself. So imagine if you want to do simple or complex add operation. So you need to read the operand from the memory, the second operand, and then do the add operation at the processor side, and then write it back to the memory. So you're doing three read and write operations. So let's say this is single read operation is 1000x times power hungry than the complex operation itself. Then by doing 2 reads, 1 write, you are consuming 3000x more energy than the addition operation itself. So this motivates us to try to come up with a new solution, for example, to do the addition inside the memory, where you don't need to move the data, or you need to move it a little bit. So rather than having those systems, you can have this kind of heterogeneous architecture. So if you need to accelerate for some specific encryption or encoding, decoding, you can send it to the FPGA accelerator rather than the processor or the GPU and so on. All right, so before moving to this, do you have any questions? No questions. Okay, sounds good. So in this course, seminar Computer Architecture, we are going to cover fundamental and cutting-edge research paper in computer architecture. You will see very old paper as well as very recent paper, and some of them are from our research group, Safari at ETH. Multiple components that are aimed at improving students' technical skills in computer architecture, critical thinking and analysis. You are going to analyze those papers. You will present one paper, but you are going to read almost all the other papers to prepare a question for the presenter. You are going to prepare a technical presentation of the concept and the strength of other works in both spoken and written forms. So you are going to prepare this presentation slide, and then you are going to lead the discussion and then prepare a synthesis report for that. So you'll be very familiar with the key research direction and different topics in computer architectures. So the key goal of this course is to educate you how to rigorously analyze, present, discuss paper and the ideas in computer architecture. How to achieve that goal? So we have responsibilities for the presenter as well as non-presenter or the audience, which is all of you. So as a presenter, you need to read, absorb, read more, not necessarily to read the paper itself, but you are going to read many other references next to that paper to support the ideas you have or the strength or maybe the weaknesses. You are going to critically analyze, think, and synthesize many papers, prepare a clear and rigorous talk, and then present it to us. After the presentation, you are going to answer some questions from the audience, and after the day of the presentation, you are going to lead the discussion online through the Moodle. And at the end of the semester, you are going to analyze and synthesize everything during the seminar course. And same responsibilities for participants. You need to read or skim those papers before the presentation, then prepare your questions, maybe ideas, maybe just suggestions for improvements, and ask them during the presentations. So after the presentation, same thing, you need to ask your question through the online forum for that, specified for those for each single paper. As well as you will write your questions, maybe ideas, maybe improvements in the synthesis report. So we try our best to cover a wide range of topics in computer architecture, starting from hardware security, architectural accelerations for specific applications such as bioinformatics, and we have 2 papers for that, both of them authored by our research group. We have many more about memory systems, interconnects, processing inside memory, and various fundamental emerging ideas, paradigm in computer architecture, hardware, software, code design as well. Sounds interesting how you can specialize architecture for small problems or huge problems, and you can gain huge benefits compared to general purpose processors. We have many more topics: fault tolerance, energy efficiency, heterogeneous parallel systems, and new execution models. So some other goals of this course is to teach, enable, and empower you to think critically, think broadly, and learn how to understand, analyze, and present a paper and ideas in a conference setup. So you will get familiar by the end of this course with key steps in doing research. So we're not teaching you how to analyze papers critically, but also you may develop your own ideas that you go for a semester project or maybe master's degree with Onur Mutlu. You will get familiar with key research directions, so you will have good knowledge about many different topics, so you can pick the one that you are interested in and do further research about it. All right, so this is the cycle of scientific research. It's not related to computer architecture, of course. It's related to all kind of research field or scientific field. So basically, you start by reading a paper, something attracts you, and do critique for this paper, understand the problem basically critically. And based on that, you'll see something that really attracting you, then you start thinking about it, whether this is a valid solution, can I do something better than that? And then brainstorm about the problem discussed in these papers. Then you'll try to evaluate the new ideas you come up with and develop new out-of-the-box ideas. For sure, research meant about collaborative hard work. So you need to collaborate with more researchers, for sure, advisors, and many other in the team. Once you get good results, you need to educate the others about your findings and results. So you need basically to publish those in a paper or in a good venue. And the cycle continues this way. So now about the logistics of this course. Any questions before moving on? All right. So this course is given by Professor Onur Mutlu. Unfortunately, he's not with us today. He's presenting in the United States, but he will be sure here in the next meetings. So he has been with the ETH for more than 4 years now. And he's a professor in CMU as well. And he basically is interested in many research areas, starting from computer architecture, of course, computer system, hardware security, and bioinformatics as well, and many more. We have 2 lecturers for this course. One is here, and me, Mohammed Alsar, and we have 6 TAs for this course. I think they are here. We have John, Hassan, Louis, Nika, Ivan is not here, Ira is not here, okay. Yeah, so basically you need to know them and know the research that they are working on. Why is that? Because they are going to mentor your presentation. So you are going to meet with them at least twice before you present. And you may find some of your papers you are going to present that they are one of the authors. So they are the best people to help you on that topic. So what we expect from your side, you need to attend, basically, all the lectures. And we have a sign-in sheet. Maybe after the break, we're going to distribute it. And each student will present just single paper. Easy, right? Simple. We have about 22 students, so we will have 22 presentations during the course. So you'll be responsible for the presentation as well as the questions, answering the questions during your presentation and the discussion afterwards. Non-presenters, you are all of you responsible preparing questions for the presenter, reading the paper, maybe just skimming over it. And as well as participating in the online discussion. So at the end of the semester, you need to write a synthesis report. It's very simple. You need to answer basic questions such as what are the papers you like from the entire course, why you like them, something like that. And if you can categorize or cluster those papers into different 4 topics, 5 clusters, what they would be and why you select those topics, What are the ideas you may develop out of those papers, and so on? It's very simple questions. And if you really attend those papers, those presented papers during the course, then it will be very simple to answer those questions maybe during the semester. You don't have to wait until the end. So we already upload a sample for this synthesis report. We may change the question a little bit, but basically the general view of this report will remain the same. So you can check that online. And this is the web page for this course, where we upload basically everything, all the materials related to this course, announcement, due date, and so on. So please check it frequently. So yeah, we have the first homework for you. It's very basic. You need to introduce yourself, why you're taking this course, etc. Just a few questions, just answer them. And please submit your answers before the end of 25th February. It doesn't take you like, I don't know, 5-10 minutes to answer those questions. But if you didn't submit this on time, then we cannot schedule for you for a presentation. So this means you are dropping the course. And please fill your interest or preferences for papers that you feel really like to present them and develop ideas, review them, and so on. So you need to do this before 25th February as well, before the end of 25th. So please do this as soon as you can. You have the list of papers uploaded there in Moodle. So you select 5 papers, you rank them from 5 to 1, and we will try our best to accommodate you for the most preferred paper you selected. But no promises. All right, so the next slide is how you are going to deliver a good talk, basically. So you start first with the title of the paper you are reviewing, the author list, full author list, and the venue where this paper presented. So it has been presented in a good conference, good journal, top journal, Nature, maybe. So this venue actually attracts the audience to pay attention to this paper. When I heard this paper was presented in top journal, top conference, so for sure this means this very good paper really makes difference in the field. So you start after that with a summary, where you summarize the problem of this paper trying to solve. Maybe if the problem, maybe if the audience are not familiar with this problem, you may go through introduction first. What are the key ideas of the paper, key insights? What are the key mechanisms and how they implement it, whether the contribution was in the implementation level or the idea or the architecture side and so on. Then what are the key results? So by designing this new architecture, they are able maybe to gain 100x, 1000x of speed up or reducing the energy consumptions and so on. And the key conclusion of this paper. The third thing, you need to mention the strength of this paper. For sure, this paper has some solid contributions, some strength where they develop new mechanism to evaluate, or they have new workload characterization, for example, and so on. Weaknesses. So this is the main important part. Some of the papers not clear where are the weaknesses. So you need to critically think about this paper. And this basically will be your main contributions, where you show the weaknesses of this paper. You don't have to be scared from this, because many of the papers, especially if it is published 10 years ago, 5 years ago, you will see some papers that cited this paper, and basically from here, where you can extract some weaknesses and develop upon those points. For sure, all papers have some weaknesses. This is for sure. That's why the cycle of research is continuing, right? Someone will pick those weaknesses, develop new idea to solve that or tackle this problem, and then publish a new paper based on that. Then you're going to summarize the thought, some ideas based on those weaknesses. So in weaknesses part, you explain the weaknesses of this paper, and here in this section, you give some thought on how we can solve it. Maybe some other papers who solved this problem already, then you need to explain that paper as well. That's why you're not analyzing single paper, but you may go beyond that, many more papers. Any question? Okay, cool. The key takeaways of this paper, you learned what you have learned so far. Enjoy the paper, you like it, you dislike it, you find the solution. Very simple to a big problem and so on. Here you will open the way for audience to ask you questions and answer them basically. And after that, you need to have your own questions for the audience. So you will, it will be both ways a discussion. So you will prepare your questions as well as answers to potential questions from the audience side. All of this should be very short. So we are limited by time here. So basically you have 15 to 20 minutes to prepare all the first part, which is problem, goal, key idea, solution, novelty, mechanism, implementation, major results, and conclusions of the assigned paper. And then you have 10 to 15 minutes for the critiques. So you have the strength, weaknesses, alternative, new ideas, and maybe potential problems that this solution creates. So they may solve some problem, but they may increase the power consumption, or they make something inefficient. And you have 15 minutes for the discussion. So basically your presentation will be around 30 minutes, and then 15 minutes for the discussion and the feedback from Onur Mutlu as well. And then we are going to take a break, and after that, the next paper starts. So we'll have basically two papers presented every session. All right, so here are more advices on the paper review talk, which you are going to prepare. You have to be very critical when you're analyzing the paper. So you cannot say this solution is good. You need to say why it's good, why it's bad. And you need to bring solid strength, solid weaknesses, not just badly written and all those rat holes. We're going to go through them in the next few slides. Always, you need to think about how you can develop better solutions. So for sure, there are some ways to improve some part of the architecture or the proposed solution, reduce the cost of that solution. The solution could be very good, very strong, but again, creating many other problems that wasn't before the solution. Of course, you need to question this problem as well as the solution. For that, you need to read background, maybe very recent papers about the same problems tackled by this paper. And yeah, this is basically part of the cycle on how you develop yourself as well as doing a contribution to the field of interest. So there are a huge number of review are published online, how to review papers or maybe the review itself about specific papers. So those can be a good resource for you. This is very important, the rat holes. And this is basically from this book. This is a very nice book, The Art of Computer Systems, Performance and Analysis, where you have techniques for experimentally design, maybe evaluate some method in the field. And the author of this book mentioned this. So you need to avoid the rat holes. Rat holes mean basically you can discuss something, but you can discuss it forever. You never reach a conclusion. So those points or those rat holes, you need to avoid them basically. Some of those rat holes, for example, the workload. Yeah, sure, you can always argue that the workload wasn't comprehensive enough. none of the existing paper can evaluate all existing workloads. For sure, they can have this workload, machine learning, bioinformatics, many other big data field. It's good to mention it, but yeah, please move on. There are metrics as well. So energy consumption, cost, noise, reliability, security issues. Yeah, mention them, please, but you need to move on. Don't focus the entire review on those points. Configuration details, parameters, he didn't specify all parameters and so on. All those are rat holes. So you will never reach a conclusion for that. And the author of those paper never satisfies your demand for those points. You ask them to try with this parameter, this value, and so on, but they could do it. Next time, you could ask for many more. This is another resource for you where you can find tips on giving clear talks. So those are part of the advices or the tips provided to you. So every sentence matters. So don't just copy some sentences or paragraph from the paper and you don't know the meaning. You have to maybe rephrase them in your own way. It's okay. You can clarify them more, cite more papers. You need to convey this message to the audience, basically. So if you are discussing bioinformatics problem, for sure, some of the audience may not be aware of this. So you need to introduce it very well. The audience normally prefers to not think. So when you explain something or you show a slide, you need to be 100% sure or 99% sure that this figure or this slide, this diagram, this plot, self-explanatory, basically. So don't let some mystery behind the slide and let the audience to think about it. This will create a lot of confusion, and they may ask you some question. They may say you are not a good presenter and so on. So you need to be very careful when you include those kind of slides or presenting new ideas, new plot. You need to explain everything in the slide, basically. Otherwise, why you are putting this in the slide, right? Surprises are bad, basically. So before explaining something or before discussing the architecture that the author of the paper presented, you need to explain why they developed that architecture, why they need that method before explaining that method. So you need to consider that the audience is always right. This is partially correct, but yeah, most of the time you cannot blame them, because if they ask you for something and that is wrong, means you didn't convey the message very well. So again, they will blame you. So you need to be careful for those, and you need to accept those feedback from the audience, try to evaluate them. If you have a good reason why they are wrong, explain to them, and so on. So now, apart from giving good talk, there's something different. Do you know this painting? Okay, maybe not. So this is the guy who painted this in 1924. And this is, again, another totally different painting, but from the same artist. And this is painted 10 years later. So same guy, but in 1937. So you can see it's totally different concept. This is basic, and this is totally different. And this is very important, basically, for this. So you have to learn the basic principles before you consciously choose to break them. So you cannot develop something very solid, something very novel or innovative before learning the computer architecture or how the computer works and why we have this architecture for GPU, why we have that architecture for memory, and so on. So you need to know all the underlying basic knowledge before develop something novel. All right, so how you can participate in this course. Again, I already mentioned some of those points. So you need to come prepared before the presentation as a presenter as well as audience or non-presenter. So you need to read, critically evaluate the paper. For sure, you will have some concerns, some questions, some unknown point that you want to clarify more for the presenter because he already spent maybe a few weeks on the same paper and he already had some meetings with the mentors. So he already has a good knowledge about this paper. You need to think about new ideas, how you can develop it. Don't worry whether this idea is simple, is not innovative, and so on. You can mention it. Someone can contribute to your idea, change it a little bit, make it very solid. You need to bring discussion point and question, read papers, and check how this paper shape the future direction of this research. You need to be critical as well. You need to brainstorm about the questions, strengths, weaknesses with your colleague, with the presenter, with your mentors, and so on. As you have to attend all the sessions, then you need to pay attention and discuss, contribute. This will be very useful for you, for your knowledge, getting experience in different topics, as well as for writing the synthesis report. So all those things, if you pay attention during the session, the synthesis report will be very easy for you, straightforward. Yeah, we have the participation online in the Moodle as well as in class. So be prepared for that. And now for the guided talk, maybe we can take a break now. Maybe it's a good time to take a break. All right, let's take 15 minutes. All right, so let's continue now. So this is a guide for you on how to follow up with the preparation for the talk, for your talk. So basically, you need to go through this sequence. First, you need to check your presentation date. After you have filled all the preferences for the paper, we're going to assign one to you, as well as assigning the date to that. So please check the date, and then start studying the paper, create draft presentation, and then basically you need preparing a good presentation. And then start, okay, there are 3 C's of reading. You have to be careful, critical, and creative when create the presentation. So it's not an easy task, but so much fun. So to tell the others about papers that you didn't contribute as an author, it's something really interesting. So you are going to explain the ideas, the strength, the implementation of this paper, and everything was implemented by someone else. So for that, to convey a good message to the audience and present the paper in a good shape, so you need to figure out some examples, some maybe other papers that present a good example of the same problem. So audience always like examples, pictures, videos, or relating the problem to some stories and so on. So you need to think carefully about that. And you need to explain the motivation for the work, basically, when you prepare the presentation. So you need to put the paper in its full picture. So you start by the motivation, the problem by that time. Maybe you'll present an old paper that was written 50 years ago. So in that time, the demand, the requirement, the user needs was totally different. So you need to explain the full picture in that time before you start explaining the paper. And this is challenging, but again, it's so much fun. So after preparing the first draft, and it doesn't have to be in a good shape, it doesn't have to be 100% ready to be presented to the class. So you just prepare the draft, you may copy some screenshots from the paper to the slides, and then you need to start contacting your mentors that I'm ready and they need to schedule a meeting date for that. So you can do that before even preparing the draft. So just to be in advance, well prepared for that, especially if you are presenting in the first few weeks. So you have very limited time. So you may discuss with your mentor before, like I expect to be ready a week after or 2 weeks after, so I need a date in that week. And this is important to have at least 2 meetings with your mentors. This is very important. They will improve your presentation, slide, maybe weaknesses. They will give you some ideas, suggestions, and so on. And as I mentioned, most of the TAs here already authored or co-authored some of the papers in the list you have. So this is a good opportunity for you to learn from the real author of those papers. This is, I think, important for you. So the grading policy for this course. So we will give a big chunk for the presentation you will prepare. So this is an easy course. Don't worry about it. It will be so much fun. So 70% of the grade will be to your presentation. And as I mentioned, there are mentors to help you, so nothing scary here. So you have 70% for the presentation, and those 70% points will be awarded based on how well did you understand the material you presented, and how well did you present it, how well did you answer the question from the audience side, and be prepared to explain technical terms. As I mentioned, there are papers irrelevant to the audience, so you need to explain everything, introduce the topic before you start the paper itself. So this is somehow challenging, but again, you will gain knowledge for yourself by exploring those research directions. And for sure, we will consider those who presented in the first week or so, and those who present a very challenging or tough paper. So there are some papers that are very short, but explaining very fundamental problem. So to explain those papers, you need to discover many more. We will give, again, 30% for the synthesis report. So if you attend all the sessions, so synthesis report sounds like just summarizing what you have attended before. And there are 10% bonus for participation in class and through the Moodle or the online forum. So if you prepare the paper, if you prepare some questions, so it's easy to get those points. So be prepared and pay good attention to the presentation. 70%, worth it. All right, so the feedback, you'll get immediate feedback from Onur Mutlu after your presentation about the weaknesses, strengths, and many more for your talk. And if you don't prefer so just let us know upfront. But I think this is very important for both parts, the presenter and non-presenter as well. So you can learn from the mistakes of the presenter by having this kind of feedback or discussion during the presentation and after. You can, after the presentation, apart from the 2 meetings before preparing or while preparing the slides, you can also meet with your TA, discuss some questions from the audience, whether you answered them correctly, whether there are some better answers to those questions. So the expected schedule for this course. So next meeting will be as scheduled, 28 February. So the presentation will start the week after, or we will send emails for that after finalizing the assignment for the papers. So we will have about 22 presentations in total, and this is the maximum capacity of this course. Each presentation, as I said, 30 minutes, and then 15 minutes for the discussions. So we have 2 presentations per session. Again, the paper assignment is based on your preferences. So we won't enforce you to present a paper that you don't like. So don't worry about that. So just start submitting your preferences as soon as possible in order to guarantee a good paper that match your interest for you. So this is a reminder for the homework to submit it before the end of 25th. as well as the paper review preferences. And that's all for this part of the lecture. And now we are going to example review done by Professor Onur Mutlu. I'm going to display a video about that. This is just an example, and to see how well you can prepare the weaknesses, strengths, and so on. Yeah, sure, this paper will be presented, is authored by Onur Mutlu, so he is the best guy to present it and explain the weaknesses, potential weaknesses, strength of this work.
So I'll give you an example of it. I didn't time it completely, but hopefully, well, and we don't actually have enough time because it's only 35 minutes left. But let's see, I may skip some things. And this is the paper that I selected. This is not...
Can everyone see this very well? We will try to upload the slides. Maybe it's already uploaded. Yeah, so you can check the slides online on the course web page, and you can match them here if you cannot see the figures, text maybe. All right, let's go ahead.
In your list of papers. Does anybody know this paper? Probably not. Okay. This is a paper that we wrote in 2011. Basically, it's about memory interference. And I'm going to essentially try to follow the strategy that I outlined earlier, the different sections. The paper is called Reducing Memory Interference in Multi-Core Systems via Application of Memory Channel Partitioning, a collaboration between Carnegie Mellon, Penn State, and Microsoft. And this is based on my student's presentation. That's why her name is highlighted, as you can see. She's right now, well, she used to be at Intel. Now she's a researcher at Facebook. Okay, so background, problem, and goal. That's the first part, right? You got to start with that. Main memory is a bottleneck. As you know, main memory latency is long. And I'm taking advantage of the beautiful pictures that are drawn. And you can also do that, actually. You can use the pictures from presentations that you find for a paper. No problem with that, as long as you do the attribution. In this case, this is my work, so I don't need to do the attribution. Although this presentation has a mind of its own, which I need to fix. Basically, it has this automatic animation enabled for whatever reason. The animations. So how do I fix that? Transitions? Animation pan. Okay, tell me. Yeah. Just a second. This. So how do I remove the automatic animations, though? Like automatic playing? No. That's not the... Play narrations, yeah. Use timings. Okay, I don't even want the media controls. That fixes the problem. Okay, you don't want animations to have their own mind. Then while you're speaking, the animation is happening, and then it's on the 10th slide by the time you move to the second. Okay, basically the problem is inter-application interference. You have different applications, and their requests interfere at the main memory. Actually, I don't know if I covered the previous slide. Let me finish this because it moved, I think. Main memory latency is long. Because main memory latency is long, core stalls and performance degrades. And today, in today's systems, you have multiple applications that are sharing memory. Red application and blue application is an example here. Now, when they share memory, they interfere with each other. They both send requests to DRAM, in this case, through the memory controller. And these requests interfere at the main memory. And this is called inter-application interference. And it degrades system performance, because it delays the requests of different cores. As you can see over here, the red request is delayed behind the blue, and blue is delayed behind the red of different applications. And the problem is further exacerbated because we're increasing the number of cores, or they're becoming more powerful, especially in GPUs, for example, and the off-chip pin bandwidth, the bandwidth to the main memory is limited. It's not increasing as fast. So that's the problem that we're tackling in this work. Basically, the goal is to mitigate inter-application interference to improve performance. It could also have other benefits. We're going to talk about the previous approach. Most of the approaches previous to this paper tackled the problem using application-aware memory request scheduling by changing the memory controller to be more application-aware. And we're going to develop two approaches. The first one is application over memory channel partitioning. And the second actually combines the previous approach with our approach. It's integrated memory partitioning and scheduling. Okay, so background, a little bit, you need a little background for this. Basically, I think you've seen it actually in digital circuits, but you have memory controller. Memory controller controls a bunch of memory banks, and each bank is a row buffer, and data can be accessed only from the row buffer. So bank consists of columns and rows. It has a row buffer, and in order to be able to access a location, you first need to activate the row, which brings it into the row buffer. And row buffer acts as a cache, so each bank essentially has a cache that's the size of a row buffer. And today's memory controller is used, well, at that time, today's memory controllers use first ready, first come memory scheduling policy, which basically prioritizes accesses that hit in the row buffer, because that's fast. Accesses that do not fit in the row buffer are slow. You need to bring them from the bank into the row buffer. And they also prioritize older requests over others, all else being equals. So this is the prioritization strategy. The first priority is here. The second level is here if there's a tie in the row buffer status. And this is clearly unaware of inter-application interference, because it doesn't really take into account which application the request is coming from, right? Obviously, there is nothing that says application over here. So the novelty of this work is we're going to pose it compared to the previous approach. So it's novel from the previous approach because we're going to do something completely different. Basically, let's take a look at previous approach a little bit. Previous approach looked at memory request scheduling. You basically monitor the application memory access characteristics in hardware. You rank the applications based on memory access characteristics and prioritize a request at the memory controller based on that ranking. That's the idea. If an application is not treated nicely for a while, its ranking increases and it becomes higher ranked so that it gets more fairness from the system and less interference. So let's look at an example. There are many works, but this is one example. This is thread cluster memory scheduling. You have these threads in the system. Some of them are memory not intensive. Most of the time they hit in the caches, but very infrequently they send requests to main memory. Some of the threads are very intensive. You could think of this as mice and elephants. Little mice, they're not very demanding. Elephants are extremely demanding. They require more space, more bandwidth. So the previous work characterized them as mice and elephants, memory non-intensive and memory intensive, puts them into two different groups in hardware, in memory controller. It forms a non-intensive cluster and an intensive cluster, and then treats them differently. It prioritizes the non-intensive cluster, threads belonging to this. Why? Because if you actually prioritize these threads, they can make fast progress without disturbing the elephants. There are a bunch of mice that are running around. The elephant is not disturbed, right? The elephant is disturbed by other elephants that are trying to kick them. Right? Essentially, that's the idea. Intensive cluster, so basically this is a heterogeneous scheduling policy. Non-intensive cluster is prioritized. That improves the throughput because these threads actually, they just wait. They don't need to wait for their memory requests a lot if they're prioritized. Whereas if they're not prioritized, they stall behind these elephants. The elephants kill the mice. Right? That's the idea. So this is higher priority. That improves throughput. Now, intensive cluster, you need to be careful on how you handle these. These very high memory intensive threads, if you prioritize one over the other for a long time, the one that's deprioritized degrades in terms of performance a lot. So for fairness, we actually do somewhat a round-robin scheduling policy. Basically, we form a ranking among these threads and shuffle that ranking over time. That's the idea. So basically, the key idea is separate into two groups. One group you prioritize because prioritization improves performance and doesn't affect the other applications. The other group, you basically shuffle the priorities over time. And this improves performance and fairness. So advantage, this reduces interference between applications by request reordering, improves system performance, as previous work, which was referenced here, showed. The disadvantage is it requires modifications to memory scheduling logic for ranking and prioritization. It's actually relatively expensive. There are two disadvantages. One is first one. And the second one is it cannot completely eliminate interference by request reordering. Because you're given some requests, you can only reorder them, right? And the goal of this work is to actually overcome these disadvantages, and novelty comes from there. So let's take a look at how we actually approach the problem. So the first approach is channel partitioning. Basically, the observation, the key idea, the key observation that leads to the mechanism is you have different applications, but you have also multiple channels in modern systems. This gives you a new degree of freedom in mitigating interference between applications. you can map data across multiple channels. So data mapping in current systems, what happens is a red application can have data in channel 0 and also in channel 1. A blue application can have data in both channels. As a result, they send requests to both channels and they interfere in both channels, which may not be good. But you could also control this mapping through the operating system and say red application maps to this channel only and blue application's data maps to this channel. Now you got rid of interference completely. You don't need a memory scheduler now to fix the interference. Of course, it's an ideal situation where you have two applications and two channels, right? So that's the key idea, basically. This eliminates interference between applications and requests. So what's the overview? Let's take a look at it. So the goal is to eliminate harmful interference between applications. The basic idea is map the data of badly interfering applications to different channels. We're going to define badly interfering in a little bit. And the key principles are very simple. Separate the applications that have high intensity and low intensity, mice and elephants, put them in different channels such that elephants don't kill the mice. And separate applications that have low and high robot for locality, because this is a similar situation where a high robot for locality application can deny service to the low robot for locality application. So let's take a look at this pictorially. So high memory intensity applications interfere with low memory intensity applications in shared memory channels. This is the timeline over here, two different channels. If you do conventional page mapping, both applications can go to both channels, and as a result, you may get requests that are distributed like this. And this is a service timeline of the requests. Now you see over here that the blue application's request got delayed behind red application's requests in this channel and in this bank. So it finishes at time 4, and the red application's request also get delayed by the blue application's request. It finishes at time 5. Whereas if you map these to different channels, in this ideal, nice example, everything is good, right? Basically, blue application finishes much faster, its request, given request, and red application also finishes much faster. So you save cycles, basically. So that's the idea. You want to map the data of low and high memory intensity applications to different channels. But of course, you don't always have this luxury of having enough channels as the number of applications. So we're going to look at that in a little bit. Let's look at the second key insight. It's basically separate applications by robot for locality. It turns out applications that have high robot for locality interfere with applications that have low robot for locality. So this is conventional page mapping. Blue and red applications map this way. And this is the real service timeline. It turns out these are the row numbers, row 1, row 0, row 3, row 2. What the memory controller does is, remember the FRF-CFS scheduling policy, it reorders requests such that row hit requests are prioritized. So that it services these 2 requests to row 0 first, and then it requests the request to row 2 and row 3 in this bank. And these are row conflicts because there is no reuse in the row, as you can see over here. So these take longer. So if you look at the conventional page mapping, blue application finishes after 6 time units, and the red application finishes after 2 time units. Now, how can we fix the problem by channel partitioning? If we partition the applications to different channels based on the intensity of robot for locality, red application has good robot for locality, it goes to this channel. Blue application has not so good robot for locality, it goes to this channel. So you separate by that, and you get this, basically. Again, you save cycles in the blue application. In this case, you happen to not save cycles in the red application because you're doing well on that anyway in the baseline mapping. So that's the key idea. That's the second key insight. Map data of low and high robot for locality applications to different channels. So okay, now the next step in the talk is to go into mechanisms. And this may be actually a place where you spend a lot of time. Let's see how much time we spend. You don't necessarily need to spend a whole lot of time, but you need to go into some more detail. So the mechanism actually looks like this. It has 5 components. The first component is to profiling the applications to decide whether they're high memory intensity, low memory intensity, high robot for locality, low robot for locality, and then classify them into groups. That's a clustering mechanism. Partition the channels between application groups such that you minimize interference or maximize some sort of metric. Assign a preferred channel to each application. I'm going to call it a preferred channel because it's not going to be hard partitioning, because there may be many reasons why. So what if you run out of capacity in this channel? You stop using the capacity in the other channel? That may not be a good idea. So we assign a preferred channel to the application such that preferably it allocates a page from there. But if this channel is full, then you may actually allocate a page from some other channel at the expense of some interference, of course. But you don't want to get a page fault to eliminate an interference. Okay, and then allocate application pages to the preferred channel as I just described. So let's take a look at the mechanism that's proposed hardware does the profiling, system software does everything else over here, because it makes sense to break it this way. So what does profiling mean? Hardware counters collect application memory access characteristics, and we just discussed what those memory access characteristics are. Memory intensity is measured in terms of misses per kilo instruction from the last level cache. Row buffer locality is measured in terms of row buffer hit rate. What fraction of the access is hit in the row buffer? And then the next step, the second step, is classification. This is one classification mechanism in the paper. You test the memory intensity first. It could be low intensity or high intensity. For high intensity application, you test the row buffer locality, high intensity versus low buffer locality or high row buffer locality. So the applications are classified into three groups. If it's low intensity, we don't care about high row buffer locality or low row buffer locality, because it's going to inject very few requests anyways. And then the next step, the third step, now we've classified. Every application is classified into these three categories: green, red, very red, or dark red. Okay, now the key question is, how do you partition the channels among the different groups? So there are multiple steps here. The first step is to group these together and group this one. This is basically a partition based on memory intensity. So you need to allocate some number of channels to low intensity applications and some number of channels to the high intensity applications. And the algorithm that's used in the paper is to assign the number of channels proportional to the number of applications in each group. Now, this is a place where you could critically think, and maybe this is not a good way of doing it. It works in the paper, but maybe there are better ways. Right? So low intensity applications are allocated to these channels. And what happens to the high intensity ones? Now you need to distinguish between different row buffer localities, and you do that, basically. In this case, you assign the number of channels proportional to the bandwidth demand of the group. Basically, you figure out how many requests per second that each group is generating, and proportionally to that, you partition the channels across those groups. That's the idea. Now again, these are heuristics that the authors have developed, and it works well, but you could always argue that there could be better heuristics, right? And these are simple heuristics to make sure the implementation is simple. You could come up with much more sophisticated heuristics. Okay, so in the end, that's step 2, basically. Yeah, now you're done, basically, step 1 and step 2. Applications are, channels are partitioned across these application groups. Now, assign each application a preferred channel. That's the fourth step from the group's allocated channels. And the idea over here is to distribute the applications to channels such that group's bandwidth demand is balanced across its channels. What does this mean? Let's assume that you have only 2 channels allocated to the low intensity group. You basically try to ensure that the bandwidth that you are using from this channel is equal to the bandwidth that you're using from this channel. Again, that's a heuristic, right? How do you do that? You basically classify the applications in terms of their bandwidth demand in the past, and you try to allocate channels such that that bandwidth demand is equalized as much as possible. Again, this is a heuristic. There's a lot of heuristics, and that could be one of the weaknesses that you can mention, right? For example, low intensity, I actually have an animation over there. Basically, low intensity group has 3 different applications with 3 MPKIs, misses per kilo instruction. That's an indicator of the bandwidth demand. And a clustering mechanism would do this. Now, bandwidth demand over here is 4, and bandwidth demand over here is also 4. That's the idea. And you do this for the other groups also. So it's simple. Now, the final step is to allocate a page to the preferred channel. And the idea is to enforce channel preferences computed in the previous step. Previous step said, oh, this application should go here, this application should go here. Now, finally, you try to enforce this. So when do you enforce this? Well, you allocate a page when you're doing a page fault, when you have a page fault, right? The operating system allocates the page to the preferred channel. If a free page is available in the preferred channel, as I said earlier, if it's not available, then the replacement policy tries to allocate page in the preferred channel. That may not always be possible or reasonable. If it fails, it allocates page to another channel. Now, there's more detail here that's in the paper that I'm not going to discuss, but you could imagine mechanisms over here on how do you change the replacement policy. Okay, so that's the mechanism, basically. So how does it operate at a high level? Interval-based operation. It has interval-based operation. Basically, in the current interval, we perform the profiling step. At the end of the interval, we do the classification into groups, partitioning of channels, and assignment of preferred channels to applications. And in the next interval, we enforce channel preferences. So the assumption is that applications don't change behavior significantly between one interval and the next. You profile them, you figure out their characteristics. Those characteristics stay stable for a long time, such that in the next interval, next time interval, next 10 million cycles, let's say, you're fine with using the characteristics that you profiled earlier. If that assumption doesn't hold, this doesn't work really well, and that's one of the weaknesses or limitations of the work, of the mechanism. Make sense so far? Okay. So the next step, I think basically we want to also integrate partitioning and scheduling. As I said, one approach is memory request scheduling. The other approach that we just discussed is application-aware memory channel partitioning. So there's a second approach in the paper that combines both in an intelligent way. It's called integrated memory partitioning and scheduling. And the idea is very simple. It's based on some observation that's important. Basically, if an application has very low memory intensity, it accesses the memory rarely. If you dedicate a channel to that application or a group of such applications, you're really underutilizing the memory bandwidth that you have in that channel. You're wasting basically that bandwidth. You're reducing interference, no question about that, but you're wasting some bandwidth. So why waste such bandwidth if you can handle these applications in some other way? It turns out the applications also have these applications that are very low memory intensity also have the most potential to keep their cores busy. You would really like to prioritize them somehow because it just has a request once in a blue moon. And if it gets delayed significantly behind some other application, it's not good. If you service it just very quickly, it doesn't hurt anyone. This is very similar to the insight that we had in the thread cluster memory scheduling. So they interfere minimally with other applications, also prioritizing them doesn't hurt others. So the idea is very simple. Specially treat those applications. So figure out what those applications are, low memory intensity, and always prioritize them in the memory scheduler. Don't put them into the channel partitioning process even. Memory scheduler says, oh, this is a very low intensity application, I'm just going to prioritize it with a single bit. That's it. And all other applications go through the memory channel partitioning step. That's the idea over here. And the hardware cost, we're going to just look at that. So the next step in the presentation, of course, key results. Now we've covered the mechanism in some detail. And the next step is key results, methodology and evaluation. So hardware cost, the paper evaluates the hardware cost. If you just do memory channel partitioning, you just need profiling counters and hardware, no modifications to the memory scheduler. That's the big advantage compared to past mechanisms. And this is the storage cost that's in the paper. If the paper is wrong, you can say that also over here. Integrated memory partitioning and scheduling, that's the next mechanism. This requires a single bit per request in the memory controller to say, oh, this is low memory intensity, and it's not. And the scheduler prioritizes based on that single bit. The application's request is prioritized if that bit is set. So that's not a lot of cost also, especially compared to other memory scheduling mechanisms. So it's good to always talk about the methodology of the work. Basically, methodology is based on simulation because these things don't exist. And this is the simulation model, and you can better not spend a lot of time on it unless there's something really interesting. So one of the strengths of this paper is it actually used a lot of workloads, like 240. That's not usual in many cases. And it uses multi-programmed workloads, spec workloads, and categorizes them based on memory intensity and does analysis based on memory intensity. And the metric that it uses is weighted speed up, which is a measure of system throughput when you're running multi-programmed workloads. Okay, so the comparison points, the paper has some comparison points. It compares to FRF-CFS scheduler, which we just discussed, which is the baseline. It compares to some application-aware memory schedulers like Atlas. It prioritizes application with memory intensity with some technique. So you can, for example, read those papers if you're doing this paper, but you're not going to do this paper anymore. Or thread cluster memory scheduling, which we just discussed, right? I just discussed how it operates. So these are the comparison points that are evaluated, simulated in the paper. And this is the key result, basically. Don't go into a lot of results, but the key result is this. It's average across many, many workloads, as you can see, normalized system performance. This is the baseline FRF-CFS scheduler. Atlas improves performance a little bit. Thread cluster memory scheduling improves performance a lot. Memory channel partitioning, it doesn't modify the hardware memory scheduler. So its cost is lower, but it improves performance a little bit more. And if you actually integrate it with memory scheduling, in the way I described, you actually get even more performance. So that's the overall performance improvement, 11% compared to the baseline, and significant compared to the state of the art, which is thread cluster memory scheduling, but it's much simpler because it doesn't change the memory controller. The memory controller is almost the same as FRF-CFS in IMPS over here. Okay, that's the key takeaway, right? There's a lot more results in the paper, but you will not have time to discuss that. Oh yeah, this is the performance improvement compared to the state of the art. And this is a big performance improvement if it's averaged across so many workloads. Because there are a bunch of workloads where this doesn't matter, and the paper covers them also, where memory intensity is not a problem. And they're not necessarily realistic in my opinion. Okay, so key takeaway, you get better system performance than the best previous scheduler at lower hardware cost. So there are two key takeaways as I had. Significant performance improvement over the baseline, that's one. The second is better system performance than the best previous scheduler at lower hardware cost. Okay, interaction with memory scheduling, this is also another result figure that's kind of interesting, I think. This is system performance, FRCFS, Atlas, and TCM. And this is what happens if you put integrated memory scheduling and partitioning on top of each of them. So you can see that FRCFS gains a lot more than others. This is because integrated memory partitioning and scheduling, both mechanisms are designed assuming that your hardware scheduler is first ready, first come, first serve. It didn't assume, when we were designing the mechanism, we didn't assume the baseline was Atlas or TCM. If we had designed partitioning and integrated partitioning and scheduling, assuming that your memory scheduler was these, you would have made different design choices. Maybe you would categorize the applications differently, right? Because there's already categorization that's happening in Atlas and TCM that we're also doing in IMPs and memory channel partitioning. So yeah, basically the takeaway over here is, regardless of, I guess, the first takeaway, which I didn't say, it improves performance regardless of the scheduling policy. And you get higher performance improvement over FRCFS as it's designed for FRCFS. So maybe future work can actually design partitioning mechanisms being aware of the underlying memory scheduling policy. Okay, so that's almost the end of summary. It's always good to have one slide if you have time. Basically, the one slide summary is uncontrolled inter-application interference in main memory degrades system performance. This paper proposes two mechanisms, application over memory channel partitioning. The key idea is to separate the data of badly interfering applications to different channels, eliminating interference. And it also combines it with very small memory scheduling, prioritizing very low memory intensity applications in the scheduler, and handling other application interference by partitioning. And the resulting mechanisms provide better performance than application-aware memory request scheduling mechanisms that are designed so far at lower hardware cost. So we're done with the summary. That was easy, right? And how long did it take? I think it took about 15 minutes, maybe 20. Okay, so now the next part is the analysis, right? Strengths. So what are the strengths of the paper? I'll give you a lot. So it's a novel solution to a key problem in multi-core systems, memory interference. It's always good to start with the problem and solution, right? The problem is key, the solution is novel, and the importance of the problem will increase over time. Clearly, we're going to be more memory bottlenecked. So it's good to do this sort of analysis. It keeps the memory scheduling hardware simple, so it's good for power consumption. It's good for complexity. It combines multiple interference reduction techniques. This is also new. It can provide performance isolation across applications that are mapped to different channels. Now they're isolated from each other completely. The general idea of partitioning can be extended to smaller granularities in the memory hierarchy, like banks. We did channels, but channels consist of banks. Banks consist of subarrays. You could actually partition at those granularities to get even better performance, perhaps. These are I say well-written paper because I wrote it, but I hope that's true. That's usually the comment we get when the papers. I think all papers should be really well-written. But yeah, these are the benefits of the strengths of the mechanism and the idea and the problem, but this is the strength of the paper. Well-written, thorough simulation based evaluation. It's a lot of workloads. Okay. Now, you may get some of the strengths from the paper because the papers are supposed to promote their strengths, but you can find other strengths also, especially in papers that are written in the past. But weaknesses are the more important part, right? Now, here you need to be critical. I already gave you a couple of weaknesses that are not on the slide while I was going through the presentation, right? It's a very heuristic-based method. What if you use a different metric? Although it could be a weakness, but we don't know exactly because we didn't really look at the different metrics. But it's good you could mention that. Okay, so I think one of the things that I mentioned, mechanism may not work effectively if workload changes behavior after profiling, right? If your profile doesn't match the next instance, then you have a problem. This could actually be worse in terms of performance. Now, most applications are not like that, but some applications may not fit well. So overhead of moving pages between channels restricts the mechanism's benefits. So if you need to move pages, in this case, we restrict that movement. But if an application changes behavior, for example, now you're in this channel, but you're supposed to be actually in that channel, Do you move the pages? In the mechanism, there's no specification like that. But ideally, if you want to eliminate interference, you should move the pages, but that's a lot of overhead. So the idea fundamentally has a limitation. It's hard to recover from a wrong choice. That's basically the limitation of the fundamental limitation of the idea, because the cost is very high. Small number of memory channels reduces the scope of partitioning. Clearly, if you have 1,000 applications and only 2 channels, good luck with that partitioning. You don't have enough freedom. It's not easy to separate applications. So this works well if you have large number of channels, a reasonable number of channels. You could have load imbalance across the channels. The idea can cause load imbalance across the channels, right? Because you're partitioning. Yeah, that's a problem. Actually, the paper evaluates that a little bit and compares to another mechanism. Okay, the software-hardware cooperative solution might not always be easy to adopt because now you're changing both the software and the hardware slightly. That's a weakness or limitation. And another limitation could be evaluation is done solely in simulation. Now we're getting close to the rat holes. Right? You could argue that this is true, but how do you do that in real life is not easy also, because now you need to have a real system and implement this, change the hardware in a real system and run workloads. So it's not easy. That's why it's done in simulation. Evaluation doesn't consider multi-chip systems. That's true. So you can imagine many, many weaknesses, right? This doesn't mean that the paper is bad. The paper had actually a lot of impact so far. It enabled some research on this area also. But clearly, you cannot explore the whole space. Are these the best workloads to evaluate? I'll put that because the next one I'll have is the rat holes. So basically, you can always question the workloads, metrics, and configuration. And I already did that over here. I didn't say the metric, but you could talk about the metric as well. Okay, so try to avoid the rat holes, basically, because those are easy things to criticize. But some of the other things are more fundamental. Okay, thoughts and ideas very quickly, just to give you an example of how this runs. Extensions. Can this idea be extended to different granularities in memory? Does it have to be through channels? But if you have banks, partition the banks. Right? Maybe you get more freedom. You have more banks, many more banks than channels. Yeah, subarrays or even mats inside the memory. Can this idea be extended to provide performance predictability and performance isolation? Isolate a workload in some channel. How? I don't know, but these are ideas that come after reading the paper. How can this mechanism be combined effectively with other interference reduction techniques like source throttling? If you, for example, a mechanism throttles the core, if it's very intensive, does it make sense to combine it with channel partitioning? How does it interact with those methods? Not clear, but that's future work. Or thread scheduling methods. How do you schedule the threads and how do you map the data? There's a fundamental tension between mapping the data and scheduling threads. You can map the data and the scheduled thread where the data is mapped. Maybe you move the threads also. How does it interact? These are open questions. And can this idea be evaluated on a real system? If so, how? How do you build this system? Can you do it on an FPGA, for example? And will it be good enough if you do it on an FPGA, that evaluation? So these are some extensions. You could come up with many more clearly. So let's go to the takeaways. That's, I think, number 6 or number 5. Basically, the key takeaways, I've already said a lot of this. A novel method to reduce memory interference, simple and effective, hardware-software cooperative, good potential for work building on it to extend it, different structures to different metrics, and actually multiple works from other people in the world have already built on the paper. Some of them have done bank partitioning, and there's a lot more that I didn't write over here. And easy to read and understand paper. Of course, for me, it's easy to say. For you, hopefully, it will be that way also. But you don't need to read that paper. And the next step is after that is open discussion, basically. You can put some questions to spark the discussion, right? For example, you could ask the question, what are the thoughts on the previous ideas? How practical is this? It could open up discussion, right? This is actually pretty practical. People are actually doing channel partitioning all the time now. Will the problem become bigger or more important over time? That's a good topic for discussion. I think it'll become bigger over time. Will the solution become more important over time? Probably, especially if you apply it to different granularities. Are other solutions better? So these are good discussion points. Is this solution clearly advantageous in some cases? Maybe, but that's a point of discussion which we don't have time for at the moment. But that gives you an example of the review. I know I've done it very quickly because we didn't have that much time, but this is about 30 minutes actually. Now you have left room for a 15-minute discussion. Any questions? Thoughts? Yes?
You talked quite a bit about varying the granularity on the memory side. could you also think about changing granularity in the processes?
I see.
Application on the application side?
Yeah, maybe. I think if that requires more effort from the software side, of course.
Is that the problem?
Yeah, it's not. If you can do that, and if you can break the application such that all of them are similar in terms of intensity, maybe it's easier to handle at the lower. But it may be very difficult to do because in the end it boils down to the access patterns, especially robo for locality, for example. If your access pattern is fundamentally streaming or fundamentally random, and you cannot turn it into streaming, then you'll have this discrepancy, right? Even if you break it into small portions. And there will be code portions that are fundamentally memory bound and compute bound, I think.
So it's more clear distinction.
Exactly. By reducing the granularity, I think you can reduce it a little bit. But if you reduce the granularity, then the management complexity increases. Now you need to distinguish between different things. But that's a good thinking, I think. Maybe there's some granularity that works much better in real systems. And we may not be using the right granularity by just looking at the entire applications, right?
Thank you.
Sure. So this is the kind of discussion that you can spark. I like that. What else? If you have anything else. Okay, yes, one more.
I think one process might have very different kind of memory access patterns, considering a process might have like, it might be doing a huge matrix computation, which has like very homogeneous memory accesses, but then it might also access the stack at some random times for some reason, and that would be more like a nice pattern, while the mathematical expectation would be another some pattern. So maybe we would run some analysis on that and differentiate between some memory accesses one single process does.
Yeah, that's absolutely right. Basically, a process can be heterogeneous internally, and that could actually make the mechanism behave not so well. Now there's another thing that's I think two things are related. If you reduce the granularity, maybe you can fix that, as he mentioned. But also, I think this is inside the memory, so some part of the process may already fit into the caches, right? So those access patterns may be visible to the caches, but not main memory. As a result, it may be okay. But it's good to analyze that for sure. Yes?
Maybe also some of the different style of access within a process would be restricted to different memory regions?
Yeah, you could do that also. Exactly. So I think this is similar to what he said. By doing the partitioning at different granularity at the process level, maybe not partitioning the process, yes. I think that's a very good idea, actually. Not just look at the entire application, which is what this paper does, but try to restrict it to a different granularity. I like that. Hey, that's good. I think I have enabled good discussion. What else? I think we're done. Yes, one last one.
I wonder if there are cases where, for example, an application needs much memory but not intensive, like not in a fast pattern. If they could lead to the memory allocator having problems with like restricting it to the different banks, like if there are cases where the memory allocation becomes very inefficient because of this type of allocation to the banks. I see.
Basically, things are restricted to one bank or one channel in this case, and you're not utilizing that other channel.
For example, if you have problems because you don't see the memory as one contiguous region anymore, and the memory allocator is optimized for that case.
Yeah.
If you use more memory, suddenly.
Yeah, exactly. I think you need to modify the memory allocator, and the paper modified the memory allocator a little bit, but there could be more to be done. It didn't really explore the memory allocator side a lot, so you could design a different memory allocator with this mindset. So certainly the balancing of different memory regions is a problem. Different channels. Okay, I guess we're done with the first meeting then. Yes?
Do we have access to the slides?
We will put up the slides on the course website.